Hello, I'm Ryan, and I'm here to talk to you about a privacy-preserving data analytics system that we did at LinkedIn for their audience engagement API. And this is joint work with my great collaborators at LinkedIn. So the agenda for this talk is I'll be giving you an overview of what differential privacy is, a very brief crash course in it. And then I'm going to talk about what the specific application or use case is at LinkedIn in which we apply differential privacy to. And then I'll talk about the overall privacy system that we built that incorporates novel differentially private algorithms with a new privacy budget management service. So the overall mission of our team is that we want to be able to utilize maintain the usefulness of data while still protecting the privacy of users. And this seems to kind of be at odds with each other. Like we want to get the most usefulness of data that consists of individual records while still protecting the privacy of individual members that make up the data set. And there are many reasons to do privacy. There's recent regulation with GDPR and CCPA. At LinkedIn, we always think of how to be members first with any new product or feature we build. And there's existing de-identification techniques to sort of scrub personally identifying information about members in a data set. But these anonymization techniques just don't go far enough in protecting privacy of members. Cynthia Dwork, one of the founders of Differential Privacy, said simply that anonymized data isn't. And by that, she meant two things. Either one, you either have scrubbed the data so much that it's no longer useful, it's no longer data, or you've scrubbed it, or you haven't scrubbed it enough. You haven't anonymized it enough to where it's not really anonymized at all. And so even with very few features in a data set, you can uniquely identify a vast majority of the US. And there's also potential attacks that can slice and dice the data and re-identify individuals in the data set. Now, rather than sort of building techniques that mitigate all of these attacks by just putting like band-aids on each one until a new attack is invented, what's a more privacy-first approach? So here I want to talk about differential privacy. And this is something that's been around for about 15 years. And here's a very brief introduction of what it is. So imagine we have some data set X, which consists of a bunch of users' records. And we want to run some algorithm or computation on this data set. So you can think of whatever computation you want to do on this data set. Perhaps you want to run a logistic regression model on these users' feature vectors. Or you want to add up a bunch of sensitive bits about all the individuals, and that's your algorithm. No matter what you want to do something to the data set, and we want to think of what computation we do on the data. And so what differential privacy does is that it introduces some random noise into the computation. And the reason for this is to sort of hide what the possible outcome could be given this particular input data set. And so the result is going to be some output distribution where some outcomes are more likely than others. But what we want to do is run the thought experiment where we ask what happens if we were to eliminate one person's data record from the data set and run the exact same algorithm on it. So the result is going to be a slightly shifted distribution, depending on whatever algorithm and randomness you're introducing. And the amount of privacy that we say this algorithm preserves is really a function of how much these two distributions can differ. So if these two distributions are right on top of each other, you could say that Doug's data doesn't influence the outcome whatsoever. And so in terms of privacy, Doug's data is like privacy is perfectly preserved. However, if these two distributions are very far apart from one another, now you can say that Doug's data heavily influences the outcome. So for this, we say that the algorithm doesn't have much privacy. So writing that down in sort of in some mathematics, we say that a randomized algorithm is differentially private, or DP, if for any two neighboring data sets, these are data sets that differ in at most one person's record. So in the previous example, the data set with Doug's data and without Doug's data. We want to make sure that the output distribution, whether we use X or X prime, are close to one another. And this closeness is measured by two privacy parameters. One is the epsilon, which is typically referred to as the privacy loss parameter. And the delta can be thought of as like a very small probability in which, like, with probability at most delta, your privacy loss could be larger than epsilon. So there's been lots of deployments of differential privacy, and I want to go over two distinct models of differential privacy. So we can think of sort of the data pipeline as being users are generating data, and then this data is then stored on some central data center. And then this data set is used to then power some new applications at a company, such as giving informative dashboards, new data APIs, or machine learning models. And so depending on where you are in this pipeline, you might want to introduce privacy in different points. And so in the local differential privacy model, this is where we privatized data, or the users privatized data before it's being sent to a data center. And so some notable deployments of this include Microsoft with telemetry data, Google with detecting malicious home pages on the Chrome browser, and Apple with finding popular emojis in iOS. So that's the local model. In the global model, this is where users are going to generate data. This data is then stored on some data center. And then we want to build applications that utilize this data set so they can freely access this data. But we want to ensure that the application itself is privatized. So because this application could be shown outside of the company's view. So for this, we have some deployments in the global differential privacy model, including the 2020 census. Then there's Microsoft's Open Data DP project with this joint collaboration with Harvard, and also Google's open source library. So I want to talk about the specific use case that we tackled at LinkedIn, and it's called the Audience Engagement API. This is an API product that provides insights on LinkedIn engagement content, and it enables external marketing partners to analyze data about members. And this is built on top of Pinot for fast real-time data analytics. And so here's a screenshot of like what one external marketing partner might build using this API product. Now, taking a step back, let's understand the task here. We have an advertiser that can interact adaptively with an API. So they can ask one query, receive the answer, and then as a function of this query response, they can then ask a brand new query. And so this makes differencing attacks a concern. And so a differencing attack is when you ask two aggregate statistics back to back, and we know that exactly one person is different between these two aggregates, and taking the difference exposes what one person's data was, such as what are the top 10 articles being viewed among all CEOs in India, followed by what are the top 10 articles being viewed among all CEOs in India, or at LinkedIn. So you could take the difference and identify what one user, how one user engaged with articles on LinkedIn. So differencing attacks are a concern, and this is exactly why we're focusing on differential privacy as a mitigation. So we don't want to we want to ensure privacy, but we don't want to just totally ignore the real-time data analytics requirements of the product itself. So we want to still provide real-time data analytics plus privacy. And the general queries that are allowed by this API are what's called top K queries, such as what are the top 10 skill sets in a particular region, what are the top 10 articles among all data scientists, things like this, these types of queries. And so the questions that need to be addressed are, how much can a single user affect the outcome of these queries? So central to differential privacy is the notion of sensitivity. And if one user can modify the result by a lot, then we have to add a lot of noise or maybe develop a brand new algorithm. Another question that we need to answer is how many queries can the advertiser actually ask? Maybe we want to limit how many queries that an advertiser can actually make so that they don't just necessarily reconstruct the whole data set based on these different top K queries. Okay, so what I want to point out here is that there's existing infrastructure at LinkedIn that might not necessarily have differential privacy in mind. So here you can imagine we have some highly distributed data set that's across lots of data centers. And we have already this existing system that can solve the top K prime very efficiently, right, in this highly distributed fashion. And so what this top K prime solver is then going to generate is like this histogram of all possible outcomes. So if I ask for the top 25 skills, then maybe this is the result of that computation, and this can run very, very fast. And so when we want to introduce differential privacy, we don't want to think about how we could modify the underlying data set itself, because this would require kind of accessing the data and running, taking a very long time in order to run each particular query. And we want this to be online. So being able to generate these aggregate statistics, and then this is where we want to privatize and apply differential privacy just to the aggregates. So this will allow us to utilize or leverage the existing infrastructure while still providing differential privacy, rather than going in and modifying individual data records with each query that's asked. And we can think of this top K prime solver as this Pinot infrastructure, which is an open source project that that's behind lots of the powerful features at LinkedIn, such as people you may know. Okay, so here's the overall privacy system. We have a data set that's highly distributed, and Pinot is our existing infrastructure that's making sense of all this highly distributed data. And we have this marketing partner at the other end, which is accessing this application via this API. And so in particular, it's going to be asking top K queries. And we want to introduce our differentially private algorithms here in between the application and Pinot itself. Rather than trying to modify the underlying data set, we want it to be a layer on top. And so here the query will then go through our differentially private algorithms, perhaps we'll translate them, and then once we get the result from Pinot, then we will add noise in some clever fashion and give you the differentially private result. Okay, so now I want to talk about sensitivity and how much one user can actually modify the results. So for that, let's think of a particular query, such as what are the top 10 countries that have a certain skill set? And so here might be the result from Pinot, this aggregate histogram that we can query for. And we ask the question, well, what happens if we were to take one user out of the data set? Well, one user can be in at most one country, so taking that user out can modify exactly, or at most one bin. So exactly one of these counts can drop. And so in order to give you privacy on this aggregate statistic, we can just add, we can utilize the Laplace mechanism, which just adds noise from a Laplace distribution, and this will ensure epsilon differential privacy. And so this will be the result, some sort of noisy version of the histogram, and we can release like the top 10 noisy counts. Okay, for a slightly different query, same like another top K query, but let's see how much one user can actually modify this one. If we ask the top 10 skills in the Bay Area, here's the histogram that we receive. Now we run the same thought experiment. What happens if we take one user out of the histogram? What can change? Well, one person can actually have lots of different skills. So all of these bins can actually drop because a user can have every possible skill out there. So we consider this to be a lot higher sensitivity than the previous one, because a user can can modify the result arbitrarily. And for this, there's another classical algorithm called the exponential mechanism from McSherry and Talwar that says that if you sample each element in a way that's proportional to its count, then we can repeat this 10 times and give you the top 10 results. Okay, and doing this will, as long as you just release the elements in the top k, not their counts, this will ensure k epsilon differential privacy. So the amount of privacy loss, or the privacy loss parameter, has grown because we've released exactly k elements in the top k. So sort of summarizing, we can identify what our known algorithms are for user-level differential privacy to be either in the restricted sensitivity setting. This is where we know in advance how many bins a user can actually modify, which is parameterized by this capital delta. For that, we use the Laplace mechanism. Or we're in the unrestricted sensitivity setting where we have no prior knowledge. Maybe a user can modify all the bins. And so for that, we have to use the exponential mechanism to give you some bounded privacy loss. But what I want to point out with this particular, these classical algorithms is that these algorithms require knowing what the full data domain is in advance. And so what I mean by that is that if I want to know what are the top 10 countries with a particular skill, I would need to know what are all the possible countries that are out there, even if a user wasn't even, if there is nobody in a particular country. Because we have to run the thought experiment where one user can be added or removed from the data set, and when you add a user, they could add in some arbitrary country. So for something like what are the top 10 articles, we would then need to know what are all the possible articles that are available for a user to click or share or comment on. And this might just be way too large. Or maybe it's not even known in advance. We want the data set itself to tell us what are the ones, what are the articles that are most engaged. And so for this discovery portion of these algorithms, we need to do a bit more work. And so I would argue that it's typically the case that the domain is either unknown or just very large. And note that if we just run these known domain algorithms in this unknown domain setting, the mere presence of an element just tells us that one person had to have clicked or engaged with a particular article. No matter how much noise we add to it, the mere existence of it is problematic for privacy. Okay, so the algorithms for user-level privacy, I'm going to distinguish now known domain algorithms, these are the classical ones, with the unknown domain setting. And for these, we developed new algorithms last year based on the Laplace mechanism and based on the exponential mechanism, but introducing a threshold, only releasing elements that are above some threshold. And these algorithms, we wrote it in a paper that was accepted as a spotlight presentation at last year's NeurIPS. Okay, so here's the overall privacy system. We have data at one end, marketing partner, and our algorithms in between. So the top K query is going to come in. It's going to go through our DP algorithm, which is going to translate it into something where it's going to go and fetch more than K results, so such as like the top 2K, get those results from Pinot, and then add noise either from the Laplace distribution or from a Gumbel distribution, which is highly related to the exponential mechanism. And we release the top K results from that. And this will ensure differential privacy. Okay, now what happens if a marketing partner just barrages this API with a lot of different queries? We want to budget access to the marketing partner. And so for that, we also introduce a budget manager. And for that, you can think of it as like a traffic light. So we have marketing partner that's interacting with this application, and it goes, the query goes to the DP algorithms, which then goes to the privacy budget management service to ask, hey, can I run that query? It says, yes, you can, go ahead. And then it's going to carry on with translating the query and adding noise in a particular way. Maybe you've interacted too many times with it. So after a while, we get a red light that says like, hey, you've exhausted your budget. So then it tries to ask that query. It asks the privacy budget manager, can this marketing partner continue? It says no, they've exhausted their budget, and that would be the end of the session until a new session is restarted. And so for the way that we compute the overall privacy budget, we develop state-of-the-art privacy loss computation bounds, and which are go together with the algorithms that we created for this problem to give you sort of the best possible bounds that improve over existing bounds on the overall privacy loss, while also giving you algorithms that actually make this feasible. And that's it. So thank you very much.